Okay, hello everyone. So welcome to the MathSoc's revision seminar for MATH2011 and 2011. So first of all, for everyone who's watching the stream, can I just make sure the audio is okay? So is everyone able to hear me? Okay. All right. So yeah. So basically today I've written down most of the theorems and definitions from the lecture slides. I assume you're already familiar with most of these, so I'm not going to be covering them in detail. I'm still going to be focusing mainly on questions, but I will talk about some of the more important theorems. So for people watching it online, I am monitoring the chat. So if you have any questions, just feel free to ask me there as well. Okay, so otherwise we're going to get started. So today we're covering the first half of the topics. Tomorrow Gordon at the same time will be covering the other half on integrals and that sort of thing. Okay, so topic 1, curves and surfaces. So I guess this is pretty much like never asked, or okay, usually like one question, and this is in the final exam. So I think you're all probably pretty familiar with this. I'm going to skip through this section like pretty quickly. Okay, so definition. So we have a general parameterization of a curve. So from an interval, I'm sending the value to something in Rn. There's some definition. So a curve is closed if the starting point and the end point are the same. Here I should say that the interval is actually, so I is equal to AB. So if the initial value and the final value are the same, then say the curve is closed. Okay. Right, okay, and then limits and calculus for curves. So here we're saying that if we have a vector function, so in this case c, which is a curve, if we say that the limit as t approaches a exists, then what we actually say is that each of the limits of each of the components also exists. Okay, so some of the interpretations of this derivative. So we can interpret it as like the tangent vector, so how quickly it is moving along this curve as the value for t varies. So if you think of it as velocity, if the question says speed, then we're actually talking about the magnitude of this vector. And the second derivative is just the acceleration. Okay. In terms of surfaces, we've got 3 different forms. I think most of you should be familiar with this. Okay. So move on to the second section, which is on topology. I think this probably is a bit trickier, so I'll spend some more time on questions and definitions in this section. Okay, so first of all, the ball. So we define a ball around some point, some vector A in Rn to be this set over here. So I guess the reason why we call it a ball is that intuitively, if we have like this in, so if we talk about the ball in just the real line, then we have a point A over here. We can think of the ball as being this interval from A minus epsilon to A plus epsilon. This would be the ball in just the single dimensional case. If we have a ball in R2, then we're thinking of like a circle around that point A with radius epsilon. If we're thinking of it in R3, then we think of it as like a sphere. I should specify this is a dotted line. So this is a strictly less than sign, is not including the points that are distance of epsilon away. So in the case of R3, we can imagine it to be like a sphere, and higher dimensions, well, I guess we can't imagine that, but the same sort of idea. So a set of points that have a distance from A that is less than epsilon. So ball is a set of points that are less than epsilon away from A. Then another definition we have is the punctured ball. So this is the same as the ball, except we don't include the point itself. So we have this additional 0 less than this distance. So think of the ball as like, for example, this is the ball, we're excluding the point in the middle. That's the punctured ball. Okay, limits of sequences. So if we have a sequence of points in Rn, then we say that x over here is a limit if and only if over here. So if for all epsilon greater than 0, there exists some n such that whenever k is greater than or equal to n, xk would lie inside this ball. So think about it, like I think this entire topic might seem very difficult at first, but if we compare all of these concepts to the single variable case, it turns out everything makes sense. Like if you think of a single variable case from first year, you'll know that we'll say for all epsilon greater than 0, there exists that such that for all k greater than or equal to n, f of x minus the limit L is less than epsilon. That's like a definition from the first year in terms of what it means to have a limit. I guess this is pretty much the same sort of idea, except we no longer have this distance, we're just writing it in terms of the ball. This is saying this is less than epsilon. So the same definition, just that we're talking about in terms of a ball. So I guess like this is just saying if I have a limit of points, then eventually it will lie within the actual limit. So eventually we can have it inside this ball, which has an arbitrarily small radius because epsilon can take any value. So for any epsilon, then this sequence of points is eventually going to go inside this ball. Okay. On the other hand, I want to show a point is not a limit. So I guess this is for lots of different types of pressures, not just this case, but whenever a question wants you to prove something is not something, then all you really need to do is negate the definition. But later I'm going to have some examples like how do we show something is like not open or something is not closed, etc. Well, all you need to do is this is the definition for being a limit point. So if you want a definition for being not a limit point, I just need to negate this. So I change the for all to exists. I change it to for all, and so on. And I negate this, and I'm done. So that's how you prove something is not a limit point from a definition. Okay. Then we have open and closed sets. So these are all definitions that hopefully everyone is familiar with. So let's say we have some sort of set in Rn. So something is an interior point if there exists an epsilon greater than 0 such that the ball lies inside omega. So let's say we have omega, and then we say that x over here, which is inside omega, is an interior point if I can find a ball around it that entirely lies inside omega. So this needs to be exists1. So if, for example, x is like over here, then say that's a boundary point, because no matter how small I make this ball around x, it's impossible to make it so the entire ball is contained inside omega. There's always going to be part of it that is inside omega and part of it that is outside. So this would be an interior point. I think most of these definitions are like fairly intuitive. This is just like a formal way to actually explain it or like define it. So say a set is open if every point is an interior point. So if any x inside omega is an interior point, then omega is open. And then omega is closed if its complement is open. It's important to note that something doesn't have to be open or closed. Like these are not like logical opposites of each other. Something could be open and closed, something could be neither open nor closed. All of that is possible. Okay, so as I said, x is a boundary point if, no matter how small I make this radius, epsilon, this ball is never going to lie inside omega. It's always going to have a point inside and a point outside. So this is a boundary point. Okay. I said it's closed if and only if it contains all its boundary points. So generally, if you're if a question is asking you to prove like a set is closed, you should probably prove it using the fact that its complement is open. Generally, you shouldn't try to prove it in terms of its boundary because you need to argue like which points are boundary points and which ones are not, and you don't want to do that. Okay, and a theorem over here, a finite union or intersection of open sets is open, and similarly, a union or intersection of closed sets is closed. So I guess if you have like more complex sets, you can break them up into union or intersection of sets, and then you can use this theorem. Okay, so I guess we'll start off with first example. This one should be fairly simple. So from the 2019 paper. We want to use a definition to show that this set is not open. So as usual, what we want to do is start off from our definition. So for a set to be open, so we say that omega is open if and only if for all x in omega. So the definition of our previous page is that every point in omega is an interior point. And so the definition, if we go back, is an interior point if there exists an epsilon such that the ball is contained within omega. So I'm going to prove that if for all x in omega there exists an epsilon. If there exists an epsilon positive such that the ball is contained inside omega. This question wants us to prove it's not open, so it is not open. So I just need to get this statement, and so I just need to change that to there exists some x inside omega. So no matter how small I make this epsilon, so for any epsilon I choose, the ball is not going to be a subset of omega. And to prove something is not a subset of omega, I just need to show that there is a point that is, let's say I want to find a point y that is in this ball, but is not in omega. That's how I want to prove this. So that's my goal when I see this question. I want to find an x that there exists, so I just need to find a certain x inside this set. Okay, that's our set. So that no matter what value for epsilon I choose, this ball is not going to lie inside the set. Okay. Everyone good with that? Right. Choose x is equal to 1. Yeah, so someone said choose x equals to 1. That's absolutely correct. So I guess like you have to probably recognize this. Like a lot of this is fairly intuitive. Generally, if we have like a fixed boundary, like a closed bracket here, you will know that it's closed. Like, of course, that's not a formal proof. So we're trying to prove it now, but if you already know what the answer is going to be, you can use that to help you prove. Like, I know 1 is probably the point that has a problem. So I just need to find, so we need to choose an x in there so that it cannot add, so that the ball does not lie inside. So it's clear that the point 1 here is the one that has the issue. Every other point is actually an interior point. You need to recognize that x is equal to 1 is the tricky one. If I imagine this to be my line from 0 to 1, if I choose any other point, then I can find this is my ball. Remember, a ball in R1 is just a line, is just a open interval. This is my ball that lies inside it. But if I choose x is equal to 1, then no matter how small I make it, it's not going to lie inside. And then I can't choose 0 because 0 is not part of the set. Like when I choose x has to be inside the set. I can't actually choose 0. I can only choose 1. Right. So I choose x is equal to 1. This is my interval. And so let's just say that this has, so now I need to prove that there is a point in here, in this ball, which goes from 1 minus epsilon to 1 plus epsilon. I need to show that there is a point in this ball that lies outside of this set. So I think if you just look at this diagram, it seems clear to you that 1 plus epsilon is going to be the one that's larger, because epsilon is positive. So okay, but I can't choose 1 plus epsilon because remember the ball is this open interval. 1 plus epsilon is actually not in this ball. So I can't choose that. But it doesn't matter, I can choose some other point in between. Like I can choose 1 plus epsilon 2. Clearly I know that this is between 1 and 1 plus epsilon. So I actually do know that this y value, this value actually lies inside this ball, and is also outside of this interval. Because 1 plus epsilon 2 is larger than 1, it's outside the interval, so I've proved exactly what I wanted to. There's a point inside this ball that lies outside the interval. And note that it's in terms of epsilon, so no matter how small I choose this epsilon to be, I can always find this point. Everyone happy with that? Okay. All right. Then some more definitions, interior and boundary. So if I have some sort of thing, this is my omega, then the interior is just a set of all interior points. So we already defined what the interior point is, so you think of it as like all these points except the boundary is interior. But this is all fairly intuitive. So the boundary of omega is a set of all boundary points, and we usually use this notation for it. And the closure of omega is just omega itself plus a union of any boundary points. One thing to note is that a set is also closed if and only if it's equal to its closure. So if it's equal to its closure, then it's actually closed. Okay. Alright. There's some of the limits here. I'll probably skip that. I don't think it actually gets assessed very often. Okay. So limit of a function at a point. I think I sort of already mentioned this earlier, so and this is a formal definition of that. So if all of this just always compared back to the single variable case, like this bit is actually all exactly the same. All they've done is that normally we say that x, let's see, say x minus a. Like normally in the single variable case, we would say that this has to be less than delta. In this case, that's just equivalent to saying it's inside this ball. Okay. I guess one small thing to point out is actually we have the punctured ball here. Technically, we shouldn't be considering the point A exactly. So I mean the point, yeah. Okay. So that's our definition. So if this limit exists, then it actually happens to be unique, just like in the single variable case. Okay, these are a couple of limit theorems. These ones are actually quite important. So first of all, if this limit exists, then it actually turns out that each of the components of f converges to each, the limit is each of these components of B. And the second one is just, this is uniqueness of limits. So this is saying that if I'm saying that the limit exists, what that actually means is that no matter what sequence I have, so I can have any sequence xk, as long as xk converges to A, then the limit of this itself must be the same as that limit. So if we compare back to the single variable case, like what this means is, normally we say that a limit exists if, so let's say this is a function, we say that there's some sort of limit coming from the left and there's some sort of limit coming from the right. If those two limits turn out to be the same, then we say that the limit exists at that point. This is the same thing except this is in the multivariable case. So if no matter what direction we approach that point from, it equals to the same limit, then the limit exists. Yeah, I guess yeah, that's what it means. So I guess the useful thing of it is for proving that a function is like not continuous, like in the second example here. So you want to prove that this function is not continuous at this point. So proving this from the definition is like well, quite difficult. So I guess it's quite useful to use that fact I just used, this theorem. So if we say that this is continuous at 0, 0, we are saying that the limit as x goes to 0, 0 is going to be 1, which is the same as the function value. So we say a function is continuous if the limit is equal to that function value. Now, what I need to do is I need to find a sequence of points xk. So I need to find a sequence such that this sequence converges to 0, 0, but this does not approach 1. Because if it is continuous, then no matter what sort of sequence I have, as long as the sequence goes to 0, 0, then f of xk should go towards 1. So I just need to find a counterexample here to show it is not continuous at 0, 0. Okay. So exactly that. So I guess like here is where sometimes you might need to be a little bit clever, but I think most of the time you actually just consider the same examples because, well, I guess usually questions when they ask in this form, what do I want to consider? Well, I want to consider approaching along the axes. The first thing I'll consider is a sequence of points, something like 1 over k, 0. Then as k approaches infinity, this will go towards 0, 0. This is effectively approaching from the x-axis for this two-variable function. So we think of this as approaching from x-axis. And similarly, I could consider the points 0, 1 on k, which is converging from the y-axis. Like, why do I do this? Because it's simple, because one of them is 0, when I sub them in, most things become 0, and we're good. Like, let's just quickly have that as an example. Like if I use 1 on k, 0, then when I put this in here, well, y is 0, so that's 0, that's 0, that's 0. I just have 1 on k squared over 1 on k squared, which happens to be 1. So I guess in this case that doesn't help me because that doesn't show it's 1. I want to show it's something that's not 1. So that doesn't help. You can try this one as well, it also doesn't help. So I guess some of the other things I might want to try out is something like this. This is approaching along y is equal to x. Then we might find we get something different. So I guess in this case, if I put that in, so I evaluate f of xk, so I just sub these coordinates into that equation, and when I simplify, I get a limit of 3 on 2, which is of course equals to 3 on 2, and that's not 1. And so using the theorem that we had above, we will know that this limit actually is not equal to the function value at that point. And in fact, we can see that the limit itself doesn't exist. The limit doesn't exist and the function is not continuous. Because we say that this equals to 3 on 2, but earlier I showed that the other sequence actually goes to 1. So actually the limit doesn't exist and it's also not equal to this function value. Could we approach 0 plus, oh yes. Yeah, probably screen delay. Okay. Yeah, so I guess some of the questions, like sometimes you might need to look at this and be a bit more creative in terms of what sequence you think might be useful. Like instead of the question is like x to the 6 plus x cubed y plus y squared over x to the 6 plus y squared. In this case, you might consider something like, well, you see that the x is like to the 6 and x cubed, so maybe I want to consider something else like, I don't know, 1 on k cubed as a possibility. So I guess you're sort of like looking at the function itself to sort of try and guess what might be useful things to look at. That will allow you to find a limit fairly easily. I guess in the end, that's why we chose these ones. Like, these are ones that are easy for us to evaluate. Okay. Pinching theorem, this just follows, this is like pretty much the same as your one variable case again. So if within this ball around A, we have this relationship between these functions, then the limit of g and h are the same at that point, which is A, then the function in the middle must also have the same limit. Okay, so first exam question, we want to prove that this limit is 0. So I think most of the time when you have something like that's fairly complicated and you want to show its limit is equal to a certain value, most of the time you probably want to use the pinching theorem to do that. Sometimes they give you a hint, like in this case, if the inequality might be like slightly hard to find. Other times you might need to think of this yourself. So they want me to show that a limit is 0. So generally the idea is I want to, okay, so I want to take the absolute value of this thing, and I want to say that this is going to be less than or equal to 0. I want to show it is less than or equal to something else that's going to go to 0 as x goes to 0, 0. So this is generally what I want to do. I do the absolute value because, well, then I can create this lower bound of 0. The absolute value is non-negative because I already know what the answer is going to be. I know what I'm trying to get. I'm trying to get is 0. So if I take the absolute value, I know that 0 is going to be a lower bound, and then later on, If I show that this is also 0, then I'll show that this thing has a limit of 0 as well. So I think I have some sort of upper bound that converges to 0. And they've already given us this inequality very nicely, and it's not hard to see that they're very similar. As in we can parameterize. Okay, so the question is, as in we can parameterize y is equal to x as that. Yes. So I just got a quick question. So about the previous questions, I considered 1 on k and so on as k approaches infinity. If you want to, you can parameterize it as like t and t, and look at what happens when t approaches 0. Pretty much the same thing. Right, so if I use this inequality above, well, if you look at this, what's the difference? The bottom expression has an extra x. So how about I just take out the x? And look at that. And using the inequality we're given, that would be less than or equal to x. And we note that as xy approaches 0, 0, then okay, obviously 0 is going to still be 0, and the absolute value of x over here is also going to go to 0. Well, because this is like one variable, we know that the absolute value of x is continuous. I can just sub in the value 0. It's going to give me 0, and the result follows because we say the lower and the upper thing both go to 0. So the thing in the middle also goes to 0. And if the absolute value of something is 0, then the thing itself is 0. And that completes the proof. Any questions so far? Right. Okay. Yeah, so the function is continuous if it's continuous everywhere. Some product quotient and composition of functions are continuous where they're defined. I guess like more generally, you're probably not trying to prove things that are continuous by definition. Most of the time, functions are composed of like elementary functions. Never know it's going to be continuous. So pretty much everything you see in this course is going to be continuous everywhere except like certain like points where it might be a bit confusing, like that case we saw above. Something like this one here. Otherwise, most of them are probably going to be continuous. Okay. Here. Okay. A couple of theorems we have here. So the pre-image. So saying that if U here is, okay, so if U is some sort of set inside the range of, the U is inside the range of F, then, well, I guess, sorry, that's not quite right. It's just in the codomain of F, then the pre-image of the set U is defined in this way. So it's a set of points in Rn. So, well, I guess more strictly, set of points in the domain of F, such that f of y are inside U. So that is some sort of, this is my U, and this is my domain omega. Then I'm trying to find the set of points such that f map them into U. So I'm trying to find this. This is the pre-image of U. So a set of points in the omega that get mapped into somewhere inside U. Okay. And another result is that f is continuous on omega if and only if U is open implies that the pre-image is open. I think this result is also true with closed. So if a set is open or closed, then its pre-image is also open or closed if the function is continuous. I mean, you probably are never going to do the reverse implication. Like it's if and only if, but you're probably not using this to prove it's continuous generally. Okay, so suppose that omega is open. I should probably skip that one. Okay, so compact sets. First of all, definition of bounded. So we say that a set is bounded if there exists an M such that the distance from the origin is always less than or equal to M. This is just saying if I have some set, then no matter what point I have in the set, its distance from the origin is always less than or equal to a certain value. I think this definition is like fairly intuitive. And we say a set is compact if it is closed and bounded. And one of the useful theorems in here is that a function maps a compact set to a compact set if it's continuous. So a continuous function maps compact to compact. Is this 2011 maths? So this this seminar here is like a mixture of 2011 and 2011 because the content mostly overlaps. So I think like some of the content is taken from 2011. Right. Okay. Okay. So next up we have path-connected sets. So I guess again this definition itself is fairly intuitive. So we say that a set is path-connected. So like this says my omega is path-connected if I take two random points here. I can always join them up with some sort of continuous function that always lies inside omega. This is my function here. So for any 2 points x, y, I am able to find this continuous path that lies inside omega that starts at x and ends at y. So formally, this is what it is. So it takes value from 0 to 1, so that at the beginning, when t is equal to 0, it gives you x. When t is equal to 1, it gives you y. And any other t in between, you get some point that lies inside omega and continuous. Okay. And again, if a function is continuous, it actually maps a path-connected set to a path-connected set. So I like looking through exam papers, and I think like this generally when they ask about path-connected sets, it's usually fairly simple. Most of the time, you can just join them up as a straight line. So this is like a useful parameterization to remember. This is the parameterization of a line segment from x to y. So like, let's say a random question is like prove that this first quadrant in R2 is path-connected. Well, if I take any 2 points x and y, I think it's quite obvious. Like I think a lot of these questions, drawing a picture helps. Like, don't use your graph as your proof. Like, that's not a formal proof. I can't just give them this graph and say that, okay, clearly it's path-connected. But it actually helps with your argument. Like, by looking at this graph, it's pretty obvious that I can just use a line segment to join them together. And the line segment is obviously continuous, and it's always going to lie inside the first quadrant. So that's like where you begin your proof. Then you know, okay, I'm going to let my function be this line segment connecting x and y. And then what do I need to do next? Well, okay, it's clearly continuous because it's composed of these. Well, okay, I guess this is a simple linear function. It's just linear in t. I guess the other thing I need to prove is that this is inside omega for any value of t between 0 and 1. I'm not going to go for that. I leave that as an exercise, but I think that's probably one of the earlier questions you cover in class. I do have an example here which is a bit more difficult. And I actually wrote this yesterday. It's not from an exam paper, but yeah, I couldn't find anything difficult, so I decided to put this one in. What do I have? Could we also use omega is a subset of 0m? Yes, absolutely. So I think someone asked, like, can we, yeah, this definition for bounded is also saying that, yeah, so there is some value m, so that omega basically lies inside this ball. So saying omega is a subset of this is equivalent. Is there a way we could access this special definition? Okay, so all these slides are going to be posted online afterwards, and so you can all access these slides. Okay, this question is one that I made up. I didn't write the full solution. I think it is actually very tedious. I've put this here for the purpose of trying to explain the intuition behind how we can prove something is path-connected from definition. So again, like, I actually encourage you to draw a diagram. Again, it shouldn't be part of your overall proof, but it should be part of your thinking process. So to draw a diagram, my set is y plus x squared is greater than or equal to 0. We can all draw this. This This is just y is greater than or equal to negative x squared. This is y is equal to negative x squared. Y is greater than would just be this region above. So like, I guess here what you just need to think of is if I take any two random points inside this set, how can I have a function that connects them together? It's continuous and it always lies inside this set. So as I said earlier, most of the time it's a line segment. In this case, actually it doesn't work because if I take x and y, for example, to be on opposite sides of the parabola, clearly I can't use a line to join them together because this line does not lie inside the set. This part is not in the set. So that wouldn't work. Okay, so I guess in this case we just need to have something more creative. I guess does anyone have any suggestions here? So I guess like one possible way you could, maybe this is a bit hard to see, but it's definitely easy to see if you draw a diagram. If you don't draw a diagram, you're not seeing this. Well, what about do something like this? Because I know that any point here, I can always, if I draw a function, if I draw a line that connects it to the horizontal axis, it's obvious from my diagram that this line segment is always going to lie inside the set. This is always going to lie inside the set, that's always going to lie inside the set, this is as well, and they're all connected. Like still, of course, this is not a proof. This is just my logic. I'm going to write this down like more formally. But this is an example of what I could do. Now, I'm not saying it's the only solution. You can probably think of something else, but this is like a possibility. So what do I need to do next? I just need to parameterize this function here. So I've written this out partially on the slide. So I've basically split this function up into 3 bits. This is just that first bit. This is that second bit, and that's like the third bit. So think of the graph, we've got those 3 bits. I'll just parameterize the 3 of them like separately. So I guess like some tips on like how you can like parameterize it like this. Let's take this middle section and look into that into a bit more detail. Let's say I want to parameterize this segment. So let's say this here is, okay, let's just call this point here x1, y1. And this point here, x2, y2. Yeah, the x. Okay, yeah, so people in the chat got this, that's good. Yeah, so I want to parameterize this, the middle line segment. That's that segment from, okay, so if we draw it more clearly, that's like x1 to x2. But basically, how I split up the t, I want it so that when t is equal to 1/3, we have this point over here. And when t is equal to 2/3, we have this point over here. And I think I'll probably want to have it in this sort of form. So usually the easiest way is to put it in this sort of form. Okay, so let me pop this out. Okay, so I want to have a t minus 1/3 and a t minus 2/3, so that when I sub in t is equal to 1/3, this bit is going to be 0. And so this bit is going to be the important bit. So that should be x1, 0. And here I want this thing to be x2, 0. So when t is equal to 1/3, this thing the x0 basically goes away. When t is equal to 2/3, the x1 goes away. And I just need to adjust it by putting in some coefficients here to make it work out. In this case, I worked out its d values. That's the general idea. Play around with the parameterization shouldn't be too difficult to get. It's just coming up with it in the first place. I didn't write the rest of it. I guess I can leave that as an exercise. But what you want to do after doing this is to prove that this is first of all continuous. I guess that is easy. Continuous, I just need to sub in 1 on 3 to show that they're actually equal. I guess I shouldn't define like that, but yeah, if I put in 1 on 3, I'll show that this is equal to that. And when I put in 2 on 3, I also show that it's continuous. That's one thing. And the other thing I want to show is that it is in S. we said that this function that connects them needs to also lie inside S. So in that case, I need to like show that this is satisfied. Like, maybe very quickly do the first one. Like if we do this one, y is 3y1t plus x1 squared. But we know from the beginning that y1 plus x1 squared is greater than or equal to 0. That's from the fact that x1, y1 lies inside the set. Then if I do that over here, well, for example, y1 is greater than or equal to negative x1 squared. So I can say this is greater than or equal to negative 3t x1 squared. Which is of course greater than or equal to 0, because this first function is when t lies between 0 and 1/3, and so 1 minus 3t would be non-negative. And obviously x1 squared is non-negative, and so the product is non-negative. Okay, everyone good with that example? Alright, cool. So someone commented in Math2011 we learned how to draw lines. Yes. Okay. Right, I think this definition wasn't actually in the lecture slides. I think I learned this in this course last year, so I just put it in just in case. You guys probably don't need to know it, but okay, so obviously we know the definition of injective is actually just the same as in the one variable case. And it actually turns out that if a function is both injective and continuous, then what this means is that it maps boundary to boundary. So if I have some set omega, this is the boundary. Then when I apply f to it, get something different. This is f of omega. Then this boundary gets mapped to this boundary. Okay. Moving on to the next section. So now we have differentiable functions. Okay, so I guess this section is quite long. Okay, so first of all, partial derivatives. So that's the definition over here. I guess like practically what this means when you're doing a question is that you're just comparing the derivative with respect to whatever the coordinate is. So for example, the partial derivative with respect to x. Basically, you think of it as just I am differentiating with respect to x, assuming that everything else is a constant. So I ever say f of xy equals to xy, or let's say x squared y. You have a differential with respect to x. Well, I treat y as a constant, then this will just be 2xy. Yeah, so most of the time you can just do it like this. It's only if, well, again, it's very similar to the one variable case. Like generally, when we have something that's like piecewise defined, then you might want to use this definition at the at that like what's it called, at that special point to actually do it. But any other point, we can just differentiate it normally, as if everything else is a constant. But yeah, I'll have some examples on like when we need to use this definition a bit later on. So yeah, get back to that. Okay. And we have the Jacobian matrix. So if I have some vector value function, so it's going from somewhere in Rn to Rm, then this is the Jacobian matrix. Evaluate at A is equal to this. So it's just a matrix of the derivative. So f1 is just the first component of f. I've differentiated with respect to each of those coordinates, and I've done the same thing for every other function, and I've applied all of them at, I've evaluated all of them at A. Okay, so I actually haven't covered differentiable yet, that's on the next page, but if f is differentiable, then it actually means that all of these partial derivatives exist. And I guess we can say that this is the derivative of f. So we have several variables, derivative is actually like a matrix of these partial derivatives. Okay. We can go for affine maps. So basically an affine map is something that's a combination of like a constant or like a fixed point plus something that's linear. So when it's linear, means that it preserves addition, preserves scalar multiplication. And we say that something has an affine approximation if there are A and B that exist, so A is a matrix and B is a vector that exists, such that this is true. Again, if you think about this, this is really just the same as single variable definition. So we say that if there's some function f of x, then I can say that, actually no, not quite, not there yet. Let's ignore what I said. Okay, basically you're trying to approximate the function by like a straight line, or in the single variable case. Okay, and we have this form for the affine approximation. Okay, so differentiability. So a function is said to be differentiable at A if it has an affine approximation at A. So basically there exists matrix A and B such that this equation here is true. It turns out that if a function is differentiable, it turns out that if a function has an affine approximation at a point A, then we can actually rewrite it in this form. So actually A in this equation above would actually have to equal to the Jacobian at A, and B over here is actually equal to f of A minus the Jacobian multiplied by vector A, or something like that. And so we get this form. So I guess if you want to prove whether a function is differentiable at a point from definition, this is how you prove it. You prove that limit of this thing equals to 0. Where that thing's a Jacobian, and yeah. So I think this you can compare it to the single variable case. The single variable case, we can say that f of x is approximately, or at A, at a point A, is approximately f of A, so around A. We can say it's approximately f of A plus f dash A times x minus A. So if I have like this is a random function at some point over A, then this is like the equation for this line. If you think about it, this definition here is pretty much the same thing. If I rewrite this, f of x minus f dash A, x minus A minus f of A, the definitions are pretty much the same. Right? It's a affine approximation. Yeah. So I guess like an affine approx would be that. This bit here is an affine approximation for f, so that when I subtract them, then that limits to 0 when x approaches A. Alright. Everyone good with this? Alright, so we've got a past exam question. This is actually very simple. That should say 2. Okay, so find the best approximation, find the best affine approximation to this function. So all we actually need to do is use that thing that we had above. So the affine approximation g of x is equal to function evaluated at the point A, which in this case would be 1, 1, plus this thing over here. So what this is basically solving into this formula. So I need to evaluate the Jacobian matrix. So how do I get this? Okay, so this is my function. So to get my Jacobian evaluated at any point x, all I need to do is find the f dx, the f1 dx, the f2 dy, that's what I need to do. So this is my Jacobian, so I differentiate this with respect to x, a partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to x, partial with respect to y. In this case, I'm using the chain rule. Just differentiate shine and get cosh, and then multiply by the derivative with respect to x, which is 2x. So I get the Jacobian. So this is that. And then to get g, okay, I missed a step here, but I actually want to apply this at the point A. So we know the point A is 1, 1. So the Jacobian at the point A, I just need to sub in x is equal to 1, y is equal to 1. That will give me 2, 2, 2, negative 2. I'm going to sub them all in. And so g of x, remember g of x equals f of x. So f of a plus the Jacobian at a times x minus a. That's exactly what this is. Expand, simplify, and you should get this. So that's like an affine approximation. Okay. Everyone good with that as well? Alright. So some of the theorems we have. So if omega is open, then if all partial derivatives exist and are continuous, then f is differentiable. So I guess like more commonly, if you want to show whether something is differentiable, this is what you might want to do. If all partial derivatives exist and are continuous, then it's differentiable. By continuous here, we mean the partial derivatives are continuous. So it's not enough for the partial derivatives to exist. They need to be continuous in order for f to be differentiable. Okay. The second theorem here is just differentiability implies continuity, just like in the single variable example. One implies the other. Okay. Then we have this theorem over here. So we're saying that if, right, so we're looking at higher order partial derivatives. So if I differentiate, I can, so for example, I can, okay, so I can have df dx, df, well, partial, with respect to x, with respect to y, but then I can take the partial derivative again. So for example, I can say, I want to take this partial derivative with respect to y, we express it like this. But I can also do it the other way around, where I first take the partial derivative with respect to y and then with x. In that case, that would look like this. Just a quick note on the notation. Like when I write like this, it means that x first and then y. So first partial with respect to x and then partial with respect to y. That's the order. So I guess the question is like whether these two things are equal. And so based on this theorem, like these higher order derivatives are, we can exchange them. We can exchange them if all of these partials exist up to that like order. So this time looking at the second order partial derivatives, if all of them exist up to this order and they're continuous around A, then I can interchange them. For pretty much all of the purposes in the exams, you can do this because all the functions you're looking at are probably going to be continuous. Unless it seems clear that the question is like trying to demonstrate this point, which is actually the example I'm looking at next. Right. So this is a question from one of the final exams in the past. I'm going to complete these partial derivatives. And I guess if you read the entire question here, so like first want to complete the first order partial derivative, then want to complete the second order ones, evaluated at 0 to 0. And part D seems to be telling us like why did this theorem not work. So I guess like well, reading ahead is pretty useful. Like I already know what this question is trying to do. Trying to evaluate these two and they're going to give me different things. And it doesn't work because I didn't satisfy the conditions in this theorem. So I guess like part C and D in this question are actually pretty easy. Like C, you stated, that's not hard, and then D, we just need to show why it doesn't work. Well, why it doesn't work, go back to our condition. It only works if these partial derivatives all exist and are continuous. So probably one of these is not continuous, so it doesn't work. Okay, oops. In this question, I think proving the first, well, actually doing the second part is actually quite annoying. It was quite hard for me to type out actually. So, okay, complete the first order partial derivatives. Here is where you have to be careful. So, earlier I said that if we want to take the partial derivative with respect to x, for example, I can just treat this function as a function of x and like the y as a constant, and I can differentiate it like that, in which case all of you are familiar. But we have to be careful because of this point 0, 0. I have to be careful over there. Because if we differentiate this one, like normally, and then when you sub in 0, 0, you'll find that it doesn't quite work. What we want here is we need to find it at x, y equals 0, 0 using the definition. So if we try to evaluate the derivative at 0, 0, then, okay, this is definition. Definition, just from the previous slides. So I'm taking the partial derivative with respect to x. So the y coordinate, I don't care, that's just 0. But for the x, I give it h, and looking at what happens when h approaches 0. So here I need to use the definition of the partial derivative rather than just like doing that one directly. So I simplify down, and then we get 0 using this. I guess this is the important bit. And similarly, if you do it for y, you also get 0 using exactly the same method. I guess you'll see that in this expression, x and y are like evenly, they're like symmetrically distributed. The only difference is one of them has a negative sign. So it's not hard to imagine that partial with respect to y evaluated at 0, 0 would also give you the same value of 0. Okay, so that's evaluating it at 0, 0, but for any other point that's not 0, 0, everything's fine. You don't really need to go through this. This is just taking the derivative with respect to x, treating y as a constant. Like I just use quotient rule and then simplify. So I guess you can believe me that eventually you will get this. Right, so I guess in here it's not clear what happens if you put in 0, 0. Right, like how do I put in 0, 0 here? Well, that evaluates to 0 over 0. Yeah, I can't evaluate that. So that's why 0, 0. I just took the limit separately. It was much easier. Okay, and then similarly, if I take the partial with respect to x, we get this expression. I guess like in an exam, you could actually do something like this because, as I noted, they're only off by a negative sign. Like all I did to get from here to here was I actually just swapped the x and y's, and then I put in a negative sign. I didn't actually redo the calculation. Right, so I guess the second part of the question is to evaluate the second order partial derivatives at, or the second order mixed derivatives at 0, 0. So like, I've just rewritten this for you just in case you don't remember what it was. So this is the partial with respect to x. It's this. And so now we want to find this, evaluate at 0, 0. So again, you probably don't want to actually take the derivative and evaluate it. You probably just want to use the definition. Okay, so remember this is just notation for this. And again, from the definition, this means that we want to take the limits. In this case, the function is this, rather than being just f. Let's see if we differentiate this function. So from the definition, we need to do 0 and then 0 plus h, which is h. Like so. Basically the same as the previous step, finding it at 0, 0. And okay, so I've basically done that for you. So if I sub in, so this is our expression, I can sub in 0h because this is not 0, 0, right? We're only taking the limits. This is 0h, so I can sub it into this expression. X is 0, everything becomes 0 except this term. So I have negative h to the 5 divided by 0 plus h squared, which is negative h. Something must be wrong. Oh yeah, and I need to divide by h. So I have this whole thing divided by h, that will give me negative 1. So if I evaluate that limit, I will get negative 1. And I do exactly the same thing for the other case, and you will get a limit of 1. So obviously in this question, you would be very surprised if you got the same limit, because the part C and D in this question hint at the fact that these two should be different. So if you've got a different answer, you should probably go back and check it. They should be different. So and this is one case where like these second order mixed derivatives actually they're not equal. So like part C was state the theorem. This is just copied from the other slide. Why is it not true? It's not true because second order partial derivatives are not continuous at 0, 0. I didn't actually prove this because it was a bit annoying, but how can we prove it's not continuous? Well, I already discussed this earlier. You just need, so it's continuous at this point if no matter which direction you approach 0, 0 from, you get the same limit. So I probably want to find another way to approach 0, 0 so that the limit of this one is, so the limit for, what I want to do. Right. So I want to find another way so that this would be different. So let me find another example. So I guess like that's overall what I want to do. So they're not continuous, and they're not equal. That's the condition required for the theorem to be true. I'm actually not sure if they required you to actually show it in this in that year. I don't have the solutions to it. I think this question is actually very tedious, like given how long it is. Okay. Right, everyone good with that example? Any questions? Okay. Right. Next off we have chain rule. So again, like these are always confusing, but it's just the same as your one variable case. It's just written in a slightly more confusing way. Like normally you have if I differentiate of gx with respect to x, then I have normally you write it in this sort of way. You notice that that's exactly the same thing. Oh, okay. I guess they swapped around the g and f, which is a bit bad, but let me just swap that around. Okay, that makes it worse, I guess. So I guess you have something like gfx. If I differentiate that, I would have that. Well, these are pretty much the same thing, right? Just instead of writing this dash, the notation that I've used here is the d. But it's the same thing. This multiplication here is just matrix multiplication. So as I said quite a few times, if you change everything to, if you compare all of these theorems or like definitions to the one variable case, you'll find that it will become significantly easier. It's actually just the same thing. We've replaced derivative with like Jacobian, we've replaced normal multiplication with matrix multiplication. Okay. So use the chain rule to find these three things in terms of those. So I guess like this is just more practically how people like to think of it. So you can do it in terms of like using that matrix multiplication. So I guess generally if we have a function from let's say Rn to R, what was I going to say? Okay, let's ignore that. Right, so I guess more practically, if I want to find this partial derivative of z with respect to R, like I guess you could do it using this definition. I guess like another way of simplifying it, like this is just from the matrix multiplication above, but I think people generally just like memorize this method. I can first differentiate f partially with respect to u, and then multiply by du dr, and then plus partial with respect to v times dv dr. If f is like a function of like let's say 5 variables, I can do the same thing. Partial with respect to the first one, like times du dr, then partial with respect to v and dv dr, and do the same thing with like the next few ones as well. So I guess like this is sort of a useful thing to remember to take the partial derivative for things that have multiple variables. And I can do exactly the same thing for s. Partial with respect to s, I can have df du like that. And in this case, it's fairly simple. So the question wants us to express it in terms of these ones because we don't actually know them. But I know that partial of u respect to r is just 2. That's just -1. And that's just 2s. So basically, I have all of these, and I can just substitute them inside, and I'll have an expression for the first two. And if I want to find, okay, that's exactly what I just did. And if I want to find the second order partial derivatives, in this question they only asked us to find this one, the mixed partial derivative. What I need to do here is take one of the ones I already had. So I already had these two. So either I can take the first one and take the partial with respect to s. Oh, actually, yeah, technically I should use this first one because we don't actually know that we actually don't know anything about the partial derivatives being continuous. So I should actually do r first and then s. So take the partial of this with respect to s, and we have this one. And think about it, the same formula applies as what we did earlier. Like, I guess maybe it's a right. So we get this one over here, and how do I get from this line to the next line? Well, I use the same thing as above. Like, let's say I call this thing g. I can say this would just be that over here. Just like how I did in the previous question. Using these. It is exactly the same thing. It looks a bit confusing because instead of saying f here, I have this partial derivative, but partial derivative itself is just another function of u and v here. So I can just apply exactly the same thing. I'm just calling the partial derivative g. And so put it back in, well, g is the partial derivative of f with respect to u, and this is just that. And when I simplify that down, I'll get this. And again, we already know what the partial derivatives of u and v are with respect to s and r, so I can just sub all of those in and get this expression as required. I actually made an assumption here, which is that these two are equal. I think that's the only way you can do this question. Technically, we can't because we actually don't know anything about f. Yeah, but I think the s forgot to specify in the question. The question wants us to express it in terms of this one, and not the other mixed derivative. Okay. And then we've got the gradient. So I guess this is like, the gradient is sort of like the Jacobian, except the Jacobian applies for a vector value function. So if I have a function from Rm to Rn, or whatever, then I can have a Jacobian for that. But if I have a function where the codomain is just real numbers, then I can have, I call it the gradient instead. So the gradient is just this vector of first order partial derivatives. And so some other useful things to know about this is that if I evaluate this gradient at A, then that is actually the direction of steepest change at A. And the useful thing is if you have some sort of surface, like, okay, I can't draw a surface, but let's say we have some sort of surface, and I have a point here A. Then if I find the gradient at this point A, it turns out that that's the direction of steepest change, and it's actually perpendicular, or it's actually orthogonal to the tangent plane at that point. So it is orthogonal to the tangent plane at this point, and so this is an equation for the tangent plane. This is actually that. Yeah, I think it's a bit confusing that this is actually like normal to the surface. Like this is my surface. The gradient is actually normal to that. It's not like in the same direction or anything like that. As you might imagine, it's actually normal to it because this is a direction in which it's like changing. So, all right. Any other questions? Okay, I think everyone's good in the chat. Okay. Then we have directional derivatives. So far we've talked about derivatives in with respect to like a partial derivative is with respect to each of them, like x, y, z, whatever it is. But sometimes you might want to look at how fast the function is changing in some other random direction I want. And that would be your directional derivative. Oh, the battery is low. Okay, let's hope that doesn't run out. Right. So I guess this is just a definition. The important thing to note here is that U has to be a unit vector. That's the thing that you might forget. U has to be a unit vector in order for this to work. But I guess more typically, you probably won't be using this equation. You're probably using this one down here. So the partial derivative is just the gradient dot product with the direction U. Again, it's a unit vector. Okay. I don't have any questions on this. I think this is generally pretty simple. Okay, then we have the Hessian matrix. So again, this is for a function that is real valued. So it's the range is just one dimensional. So previously we've defined the gradient for these other functions. The Hessian is just this matrix of second order partial derivatives. So it's partial with respect to x1 twice, and so on. You get the point. That's the Hessian matrix. Okay, and Taylor polynomials. This part is also, I guess, fairly simple. You just need to memorize the formulas. So earlier we talked. I guess we already talked about this one. This is just the affine approximation we had. So that's just approximating my function by a polynomial of order 1 about a. If instead I want to approximate it by a polynomial of order 2, or I need to have another term over here. This is the second order term. And this is how it's written in terms of the Hessian matrix. I guess this is one way you can remember it. Most of the time when it comes up in the exam, they're probably asking for like the two variable case, in which case you can also remember it like this. Let's say it's at the point x0, y0. This is equal to f of x0, y0 plus oops. Right, these are the first order terms. Like this will just make it the affine approximation, and I need to add on the second order terms. Okay, I will not fit this here. Right, so you can have them like that as well. I think that's probably not legible, but I guess like one way you can remember this is you can actually even have higher order terms using this method. These coefficients actually just follow like the binomial, like 1, 2, 1. If I have the third order one, then you have like 1, 3, 3, 1, and divide by 3 factorial. Yeah, so I guess like this is another way. I think typically people might find this method a bit easier when we're looking at, well, I guess simpler functions of two variables. So this can run out of battery or something. Okay, I don't know. Okay, so I guess we have Taylor theorem for first order. So again, this is just the same as your one variable example. Like this first bit over here is your. Okay, so it's not like me. Let me try to fix this first. Hey John, you have wrong with the pen.
Nice.
Okay. Yeah, it's working again. Okay, so like this first bit over here is just your the Taylor polynomial of this is just the first order approximation, affine, and I've got another remainder term here. It's in the same form as like the second order term, except here we have the x, whereas here we have so there's some z over here. That makes it work. Okay, so exam question. So this one again fairly simple, just using that formula we just have. So we want to find a Taylor polynomial of degree 2 for this function around this point. So we're trying to approximate this function using the first order and second order terms. So this is just what we had from above. This is just exactly the formula. Or maybe you could use the other one in terms of, like, since this is like a 2-variable function, you might want to use the other one that I wrote down, which you might find easier. But it's actually just the same thing. So I need to, first of all, evaluate f of a. Well, a is just the point 1, 0. F is obviously this function. So f of a, I sub in 1, 0. X is equal to 1, y is 0, dash plus 0 is equal to 1. And then I want to find the gradient. So the gradient is just the vector of the partial derivatives. So I first have df partial with respect to x and y. So I just do that over here. And I should give you these this expression. So this is the gradient. And then next I want to find the Hessian matrix. So to find the Hessian, I will need to, well, if you look at the definition earlier, we can think of it as actually just coming from the gradient. So the gradient of f So I think it's coming from here, like how do I get this first term? Well, I will want to take the partial derivative with respect to x1. How do I get the second term? We'll take the partial with respect to x2, and so on. So I guess like the Hessian comes from the gradient. Like once you get a gradient, it's slightly easier. So yeah, so I already have those ones. So to get the second order partial derivatives, I just need to take the partial of this term with respect to x and with respect to y. And it's a bit annoying to do, but if you do it, you would get those. And I also take the partial of this with respect to y, and I will get that. It's important to note that this should be symmetric because we said that the mixed derivatives actually commute if the function is continuous. If all those are continuous, and that's generally true for these elementary functions. So it's certainly not a surprise to me that these two are actually the same. So if confident enough, you actually didn't need to bother doing that. But maybe you could to just check that you didn't make a mistake. Right. So that's our Hessian. So now we need to sub everything to the formula. So I need to evaluate the gradient at a, which is 1, 0. So I sub in x is 1, y is 0. And I want to evaluate the Hessian at a. So I sub in those values as well. And then I'm pretty much done. So I sub everything inside. So this is f(a), this is gradient evaluated at a, and so on. I think I might have missed the half actually. Okay, that would be a bit unfortunate. I think I missed the half. And so I think this is probably slightly wrong. Yeah, so this would be, okay, I guess the half, I guess we'll ignore that, it's more enough that, yeah, otherwise it doesn't affect anything. So, yes, otherwise it's just matrix multiplication followed by a dot product, because the result of this matrix multiplication would just be a vector with 2 components. So I just take the dot product, and I get a scalar. This is dot product, I get a scalar, adds everything together, I get like, yeah, a polynomial in x and y as I should. This is a real valued function. Okay. So everyone good so far? Haven't lost anyone? Okay. Right, next section, maximum, minimum, and saddle points. So this is again like the same as one variable case. Something is a stationary point if the gradient at that point is 0, or in this case a 0 vector. And global maximum, global minimum, those make sense. So if something's global maximum is just larger than everything else, every other function value across the entire domain. If it's a local maximum, then it's just larger than everything like around it. So there exists some sort of ball around it so that f of a is larger than f of x. And we can also have a saddle point which is something that is neither a maximum nor a minimum. So in the one-dimensional case, a saddle point would be like something like y is equal to x cubed. That's drawn a bit badly, but this would be a saddle point because it's a stationary point, but it's not a maximum or minimum. So we can also have similar sort of things in higher dimensions. Right, critical points. So a point is a critical point if it satisfies one of the following: either it's a stationary point, it's a boundary point, or f is not differentiable at that point. Again, same as like one variable. So say that's the value of x, then this would be a critical point. Say I have y is equal to x squared, that would be a critical point because it's a stationary point. Or if I define my function so it's between like here and here, then those are my critical points. So maximum and minimum must occur at one of these. Okay, so some definitions. So hopefully all of you kind of remember your eigenvalues from like first year. I think back when I did this course, I definitely didn't. So a matrix is positive definite if all of the eigenvalues are positive, negative definite if all of them are negative, semi-definite if they are non-negative, so they could be 0. Could be 0. And the same for the negative semi-definite. Okay. I guess there's one of the ways for finding whether it is positive or semi-definite. I personally don't really like these definitions of this theorem, so I'll just skip it. I prefer using eigenvalues. So I guess this is an example. So I've got this function over here, and I want to find all of the critical points and find out what type they are. In this case, it says critical points, but clearly I'm actually just looking for the stationary points because there's no boundary points. It's defined everywhere. Everywhere in R2. I don't have any points where it's not differentiable because it's just like this polynomial. So I'm just looking for stationary points. So, right, do you have a charger? Do you have a charger for the iPad? No, okay. Right, I guess we'll swap to the screen for my computer then. Okay, so if I take the partial derivatives, so not that. Okay, so I want to show out the gradient of f. I want to solve for this equals to 0. To say that a point is a stationary point if the gradient at that point is 0. So basically, I just want to solve this equation to find all of these points. So first of all, I just need to find the gradient. The gradient partial derivative with respect to x, I get this. Partial with respect to y, I get this. And now I need to solve for this equals to 0. So basically, this is just solving this one equals to 0 and this one equals to 0. Practically, you'll probably just start with this one. If this is 0, then we know that x is equal to negative y, and then I can sub that into here and then solve for whichever one, and then get the other one because it's just negative. Basically, solving these two simultaneous equations, I'm assuming that everyone knows how to do that. And so if you solve it, you get these points. 1, negative 1, and 5, negative 5. Right, so the next thing I want to do is we want to find out what type they are. So whether they are maximum, minimum, or a saddle point. So in order to do this, I need to go back to the theorem. I need to look at whether a matrix, I need to look at whether, oh wait, did I skip this slide? I must have skipped this slide. Right, so what we're looking at is the Hessian evaluated as A. Because if this is positive definite, then f has a local minimum. And if negative definite, then f has a local maximum. It's important to note that actually, if we have an eigenvalue of 0, so if one of the eigenvalues is 0, then this one here, the Hessian is either going to be positive or negative semi-definite. And based on this theorem, that actually means we don't have enough info to say whether this is a maximum or a minimum. So if the Hessian is positive definite, I actually can't say, so if it's positive semi-definite, I can't actually say f has a local minimum. It could have a local minimum, but it could also have a saddle point. I think this is generally not asked in this course, unless there's some obvious reason why you should know what it is, but generally they shouldn't ask anything that has an eigenvalue of 0. Okay, so I guess like the important thing here is I want to find the Hessian. Once I find the Hessian, I'll be able to determine whether this is positive definite or negative definite, and hence whether this is a maximum, a minimum, or like a saddle point. Right, so this is the Hessian at any point xy. I want to look at these two critical points, which are 1, -1, and 5, -5. So if I sub in 1, -1, I get this matrix. So now I need to check like whether this is positive definite or negative definite or neither. So I guess like what we want to do is find the eigenvalues. Find the eigenvalues. Well, I guess we just want to find what sign these eigenvalues are. If these two eigenvalues are both positive, then we have a minimum. If it's both positive, we have a positive definite matrix. We have a minimum stationary point. If both the eigenvalues are negative, then we have a negative definite matrix, and this will be a max. If on the other hand, these two eigenvalues have different signs, like we have one positive and one negative, it will be a saddle point. So if we have one positive, one negative, we have a saddle point. So usually we look at two things, which are the determinant and the trace. We look at the determinant, so we know that is 12 times 24 minus 24 times 24, which in this case is actually equal to negative 288, which is negative. Now, the important thing is that the determinant of a matrix is actually equal to the product of eigenvalues. You should have learned that from first year, but maybe a little bit forgotten. The determinant is the product of the eigenvalues, and the trace, which is the sum of the diagonal entries, is the sum of eigenvalues. So if the determinant is negative, that means the product of the eigenvalues is negative, which must mean that these two eigenvalues have opposite signs. One is positive, one is negative, so it's a saddle point. So I guess like probably in this course a lot of you just memorized that. Okay, people like Sylvester's. Okay, yeah. So if they all have positive or if you have one positive, one negative, it has to be a saddle point. So in general, if the determinant is negative, you would know you have a saddle point. For this 2x2 case, not for like higher ones. And then additionally, if I know that, for example, the determinant is positive, that means the product is positive. In that case, the eigenvalues are either both positive or they are both negative. But then if I also know from the trace, if I know the trace is positive, that means the sum of these two eigenvalues is positive. But if some of the two eigenvalues is positive, then that must mean that they're both positive. Because they're either both positive or both negative. That's the second example here. So if I put in the point 5, -5, I will get this matrix. So again, I want to find whether both eigenvalues are positive, negative, or different signs. So find determinant, it's positive. That means both positive or both negative. So both positive or both negative. But we know the trace itself is, where did this come from? 12 is greater than 0. Okay, we know the trace is positive, and so the sum of the eigenvalues is positive. So they have to both be positive in order to have a positive sum. If they're both negative, they'll have a negative sum. So we actually know that both eigenvalues are positive. And so this matrix is positive definite, and we have a local minimum. Okay, how am I going for time? Okay, Lagrange multipliers, I'll go through this one a little bit quicker then. So, okay, so Lagrange multipliers, this is basically when we're trying to find the maximum and minimum values that a function attains, subject to some sort of constraint. So, subject to some sort of constraint, we want to maximize and minimize f. And so it turns out that these critical values, or these points, appear when this condition is satisfied. So when the gradients of f and the constraint evaluated at that point A are parallel, as given by this. So I think typically these questions more or less follow the same method. So I want to use the method of Lagrange multipliers to find the maximum and minimum values of this function, subject to the constraint that we're on this sphere. So basically, this function is getting evaluated inside on this whole sphere, and we want to find where does it take the maximum value. So first of all, we just need to find our constraint. This is our constraint. Usually, we want to put it in the form of okay. So this is my g of x. So my constraint is g of x equals to 0. Technically, it doesn't matter whether I minus the 14 or not, but I don't know, I think that's just conventional. So this is my constraint. And I want to find the points where this is true. So I need to find the gradients of f and g. That should be fairly simple. And then we want to check that, okay, this is an additional condition that actually we require. We have to make sure that the gradient of g is not 0 for any point on the constraint. Otherwise, the method actually doesn't work. So generally, you should also make sure you check this. So if I want to check this, what I need to do is make sure I make this equal to 0, 0. And I find out that the only point that satisfies this is 0, 0, 0, which is clearly not on the constraint because it doesn't satisfy this equation. So we don't need to worry about this problem. This problem is gone. We can just proceed normally. I want to find the point such that this condition holds. So they are parallel and the constraint is satisfied. So now we just basically get a bunch of equations. How did I get this? Well, I had the components of okay, so we go back delta f. Gradient of f is equal to 2, negative 3, 1. And then this one is equal to 2x, 2y, 2z. So if I equate them, then 2 would just be equal to lambda multiplied by 2x, negative 3 is equal to lambda multiplied by 2y, and so on. And so I get this following set of equations, and all you really want to do here is just to solve for the set of points x, y, and z that satisfy this equation. Typically, the easiest thing to do here is just to put x, y, and z in terms of lambda, and then sub them in here. So I want to put x, y, and z in terms of lambda, and then sub into this equation. Then I will be able to solve for lambda. Once I solve for lambda, I will easily be able to get x, y, and z. That's probably the easiest way to solve it. So yeah, because lambda is not 0, I can divide everything by lambda. Well, if lambda is actually, yes, I can divide by lambda, and we get all of these. And then I sub all of these into the constraint, and then I can solve for lambda equals to plus or minus 2. Sub them back into here. I can get, well, I guess to here. I can get the coordinates of x, y, and z. It turns out that we get 2 points, which turn out to be plus or minus of each other. So these are the 2 points that satisfy the condition. And so any maximum or minimum value must occur at these points. If I now apply the function at these points, I will get plus or minus 23 on 4. And so one of those would be the maximum, the other would be the minimum. So the maximum value of the function is 23 on 4, and the minimum value of the function is negative 23 on 4. Yeah. Okay. So I guess I'm moving on to, alright, so there's also inverse function theorem. This is, again, pretty much just the same as the one variable case. Okay, so the last section we're looking at is the integration. I guess first of all some definitions in terms of how it works, but this is almost never assessed. So it's more or less here just for reference, so you can look at it look at the slides when they get posted, but I'm not going to cover this section. Okay, so in terms of these regions, we have, well, most simply, we have something like a rectangle. Make it more complicated, we can have what we call y simple or x simple. We can express them in two different ways. So I guess like probably just have an example. Let's say this is y equals to x squared. So let's say the question says that we want to integrate over this area that is bounded by the graph y is equal to x squared, the x-axis and the line x is equal to 1, basically this area. And basically I want to integrate over this area. I would first need to be able to express this region in this sort of form. I can make it x simple or I can make it y simple. Let's just use an example to see how we can do either one. Let's just say we want to say y goes from 0 to 1. So say y goes from, sorry, wrong thing, start with x. Okay, so when x goes from 0 to 1, as that happens, our y, well, we know that y eventually goes to 1, but like, as we go along the x, the y value only goes up to x squared. So y actually varies from 0 to x squared. So I guess we can describe this region as a set of points x, y, such that x is between 0 and 1, and y is between 0 and x squared. Because this value here is, if I have a value here, x, that would be x squared. And on the other hand, if I want to write this in a different way, if I want to write this so that it's y that's between 0 and 1, and x is something that varies, something that is bounded between functions of y, well then I can draw another line instead. Let's use green, something like this. So for a certain y, x varies from this point over here to 1. This point over here, x is just the square root of y. Taking a positive root because we're looking at the y in the first quadrant. So we'll just say that x varies from root y to 1. So I guess this would be like another way of describing the same region. So often there's probably one way that is more convenient than the other, and you probably want to use that. Yeah. Okay, some properties of integrals, these are like mostly the same as the one variable case. So we'll skip that. Okay, and in Fubini's theorem, this is, I guess, fairly important. So it means that it's saying that if a function is continuous on a rectangular domain, then we can just swap the order of integration. The idea applies for like more complex regions as well. You just need to like do what I did here. So if a function is given to you as something like this, then you need to realize that this integral is describing this region. And then this region can also be described in this way. And so I can rewrite this as going from root y to 1. So this is y dx. So x goes from root y to 1, and then y goes from 0 to 1. So I can swap the order of integration, but I need to like make sure I describe that region properly. And this can actually be, so sometimes rewriting it like this can make the integral much easier to solve. I think usually probably question will give you a hint that this is good. Okay. Right. Okay. Then we have Leibniz rule. So basically we have this thing over here. You probably know that this thing here is something looks wrong here. I think these are swapped around. There's only one. Right, there's extra. Okay, rewrite this. This should be just dy. Okay, so basically, if you integrate this function, basically the y disappears. This is just a function of x. The y has gone on to do the integral. And so it's actually possible for us to just find the derivative of g without worrying about integrating this first, using this rule. There are some conditions on the top for like when this is true, but I guess like generally most examples you have in your exam should allow you to use this formula directly. Yeah. So I guess we have an example. We want to calculate this. So again, this thing here would be a function of x because the y disappears. Y is just the integration variable, it's gone. So I need to apply this formula over here. I will take the derivative. Well, I guess a good thing here is that phi to x is just x, and this one is just 0. I guess that makes life much easier because, well, I suppose this term here just disappears. That's just 0. Actually, was it 0? Yeah, it was 0. Yeah, and so we've only got these two terms left. And this term also happens to be 1 because it's just x. So hey, derivative is just 1. So I just sub directly into that formula and I will get this. Right, so I get that, and so on, using the formula above. So I need to take the derivative of this with respect to x, and so I treat y as a constant, so I only treat this thing on top, differentiate sine, I get cos, multiplied by the derivative of the thing inside, multiplied by y, which cancels off at the bottom. So differentiate this thing is y cos xy divided by y, which is just cos xy. Okay, let me get this over here. And the rest of it is just, well, I guess like simple integration, which we can skip. Okay. I think this is probably one of the last sections I have. So looking at change of variables. So if I want to change the variables I use, I guess this is more clear when we actually do some examples rather than just looking at the theorem. What you just need to do is multiply. Okay, yeah, that eventually came. Right. Let's see. I think I had that. Yeah. Okay. Let me just make sure that goes in the string. Okay. Is it getting streamed? Oh, not yet. Okay, it's working.
Just looks like open and close sets.
Oh, okay, yeah, I've changed it. It should be good then.
So you zoom out of it.
Oh, okay, right. I need to resize it. Okay, that's a bit big. Okay. Right. Okay. That should hopefully be good. All right. So if I want to, let's just actually make sure. Yeah, it should be good. Okay. So in terms of doing change of variable. Okay. Yeah, it should be fixed now. Right. So to do substitutions with several variables, I need to also multiply by the determinant of the Jacobian. Often they just call that the Jacobian without saying the determinant, but we actually need the absolute value of that. So I guess one specific case of this that you should probably remember is doing polar substitution. So polar substitution will sub x is equal to r cos theta, y is equal to r sin theta. So those are the coordinates of like on a circle. Where y, okay, well, in that case, the Jacobian determinant is r. I don't believe you need to prove that. You can just like quote it directly. So when I'm doing a polar substitution, this term over here, the determinant of Jacobian is just r. And I write everything else in terms of r and theta. Okay, I do have one example here, which is from a past exam question, asking you to make a substitution. Well, actually, I guess the question itself doesn't ask you to make a substitution, but you probably need to do one to actually do the question. So basically, we want to find this integral. Well, I guess the integral itself is pretty easy. We just care about like what the region is. That makes it a bit more difficult. And I guess our main difficulty here is to express this double integral as like well, two repeated integrals that we can like do normally. So I guess the first thing you want to do is to actually draw up this region. So it's the region that's bounded by the curves xy is equal to a half, xy is equal to a 2, and the lines y equals x on 2, y equals to 2x. So why do we want to use a substitution here? Well, I guess technically you could do this using methods from earlier. Like you could probably have like an x simple or y simple one, but I'll need to break it up into many components. I don't think the functions you get there are nice either. If you do like that, it will take you like an hour to do. If you're, and you'll probably make a mistake. So I guess like a simpler solution here is actually you could make a substitution. So I guess like part of it is like the idea behind the substitution. Like how do we choose what substitution we make? Yeah, I think this question actually didn't give it to you. I think usually they probably will. I guess like one example we could do is that this bit over here. xy varies from half to 2. But however, I call that u. If I make my u equals to xy, then my u would just vary from half to 2. That would be very simple. And I can just call my other thing, which is v, I can just call it whatever I want. And usually we might say something like v is equal to y. It doesn't matter, you can make v equals to x, it will work. You can probably make v equal to a lot of other things. But y or x, those are simple things. So the important thing is why I choose u is equal to xy, because when I chose that, then this first bit over here will just be u is between half and 2. And then I can probably write v to be constrained by like 2 functions of u. And if I can do that, then that's in the form I want. I know how to write that out as a repeated integral. So, okay, I've got u and v, that's how I have defined them. That's my substitution. Then what I want to have is express x and y in terms of u and v. Why do I want to do this? Because I want to calculate the Jacobian. So to calculate the Jacobian, I need to, it's this matrix. So partial x with respect to u, and so on. So looking for our definition, x is actually u on v. So if I take the partial with respect to u, then I'll get 1 on v. Take the partial with respect to v, I get negative 1 on v squared. And then y is just v. So partial with respect to u is 0, partial with respect to v is 1. This is my Jacobian matrix. I want to have the determinant. So a determinant is 1 on v times 1 minus 0. So the leading diagonal and multiplied, subtract the other diagonal multiplied. And we should take the absolute value. In this case, we actually don't care because you'll see that our v is equal to y, and y actually only takes positive values. So we actually don't really care. I can just, well, this is already absolute value. Okay. So now I need to actually substitute in, okay, well, I guess now I need to work out how do I discuss this region in terms of u and v, rather than x and y, because now I'm integrating with respect to u and v, and my region needs to be described in terms of u and v. So I already talked about the first thing, that was easy. Xy is between half and 2, well, my u is xy, so now it's just u is greater than or equal to half, but u is less than or equal to 2. That's one of it. I also need the other one, which is this one over here. Right now it's, well, what can I do? I already solved for x and y in terms of u and v, so I can substitute that in. Then I'll have another constraint that involves u and v. If I just do that, I'll get this over here. That's just subbing x and y into that original constraint. And if I simplify this a bit, let's say I multiply through by v. V is positive, so I can do this without any problems. Then I'll get u on 2 is less than or equal to v squared, which is less than or equal to 2u. And then again, they're all positive. I can just take the positive square root, and this is my constraint. So this is actually an equivalent way of describing that region we had above. So originally we described it in terms of x and y, but now we just described it in terms of u and v in this way. And right now it's like, it's simple because u only varies from half to 2. This one is like some, well, it's bounded by 2 functions of u. We know how to do this integral. So I first integrate back to v and then u. So v varies from root u on 2 to root of 2u from over here, and then u just varies from half to 2. And originally the function, if you remember, was x squared. All I need to do is sub in x is u over v. So this is my x squared. And remember, I also need to multiply by the Jacobian. So I also need to multiply by 1 over v. And the rest of it should be pretty simple. The rest of it is just doing integration twice. So this is 1 on v cubed, so I get negative, okay, I think a factor of, okay, a 2 is missing over here, but it's not missing from the next few lines, so that's fine. There should be a 2 over here. And the rest of it is just evaluating simple integrals. Okay. Anyone have any questions on that? Is implicit function and inverse function theorems in here? Yes. Yeah, I had it somewhere here, but I think I just like sort of skipped over the inverse function theorem because I thought it's yeah, because I didn't have any questions on that. It's mostly the same as the one variable case. Implicit function, oh yeah, I think I did miss that one. I was going to put it in, but then, oh yeah, right, I don't have that one here. Okay. Yeah, so I guess otherwise, like, that's the end of this half of the course. So tomorrow, Gordon will be covering the other half. I guess, like, does anyone have any final questions? All right, then I guess in that case, yeah, thanks everyone for coming. Come again tomorrow to watch the other half.